Greetings from San Francisco, MATSE 112. I'm sorry I can't be with you today, but I'm sure that you're in good hands with Clara and Raymond. They'll guide you through class today. Hopefully they're showing this video. They'll also give you a short quiz on paper that they'll collect just to make sure we're all on the same page after the first week of class. And then finally they'll give you some time to connect with your teams and work on your assignment in preparation for Friday, when the assignment is due on paper in class, and you'll see that in Canvas. So to start off, this is the beautiful morning San Francisco skyline. You can see it's still a little hazy out there, but if you want to talk about traveling around the world and doing science, I'm happy to tell you some tales on Friday. So what I want you to think about in class today and over the next couple days, and we'll also cover quickly on Friday, is I want you to think about van der Waals forces and some observations of what they are. So that's covered in this slide right here. And so think about these different points. Van der Waals forces are always present. They're usually attractive. They're longer range than covalent bonds. And you can see the other points right here. And this slide is in the notes. And so we really want to think about how van der Waals interactions control the behavior of materials. And in order to do that, we need to dig a little bit deeper into how to describe van der Waals forces, what they are physically, and how we use them in day-to-day life. So I want you to, again, we've talked about this in class previously, but the interaction of two atoms is really due to the electrons. And so we can draw an idealized picture of electrons interacting, and you see the nucleus as well. This should look familiar from the in-class notes. But what happens in the interaction of these electron clouds is that we get induced dipoles. And so these induced dipoles are what cause attractive forces between molecules, and this is why van der Waals forces are generally attractive, because every molecule undergoes induced dipole. And once we have a positive and negative induced dipole, those can cause the molecule to become attracted to one another. So we also know that electrons move very quickly, and so these induced dipoles oscillate very, very fast. So on the order, in this slide it says on the order of 10 to the 15 times per second. So these electrons are moving around very quickly, and so the induced dipole is a very, very fast phenomenon. And this is what gives London dispersion forces, these induced dipoles. So we've talked a little bit about polarizability and induced dipoles in previous lectures, and I just want to remind you the difference between polar and polarizability. And so you can take a look at this slide and you can see we have a polarizability series starting with hydrogen, H2, and going all the way down to iodine, I2. And so we have increasing polarizability because we have increasing electrons in these compounds. And so we have the soft, squishy electron clouds. Now on the other hand, we have polar molecules, and so we have an imbalance in electronegativity. The molecules are not symmetric, and so they have a permanent dipole. And so you want to think about the difference between an induced dipole and a permanent dipole, and what the shape of the molecule is and how you tell. So take a look at those slides. We will also cover what a dipole is. We want to be able to calculate dipoles, and so the units of dipoles are in debye, and Peter Debye is a person. And so as you're thinking about dipoles, you can Google Peter Debye's name and see what he's done. We'll cover this specifically and do some calculations in class on Friday, but this will give you a start in thinking about what a dipole is. Okay, we're going to skip a couple slides, and we're going to think about a few different interactions between polar molecules. And so we're going to have three types of interactions. So we have dispersion forces, or London dispersion forces. Remember, every molecule undergoes London forces. We're going to have orientational forces, or dipole-dipole forces, and those are called Keesom forces. And then we're going to have the last one, which is dipole nonpolar forces, which is called the Debye force. And so these different interactions have different mathematical formulas, and we'll cover that in this lecture. So we want to be able to break down the different types of van der Waals interactions depending on what the molecules are. So here's Fritz London. He has a very nice web page, and this is the person that London forces are named from. And Fritz London is interesting because he was at Duke University, and also he worked with his brother Heinz London, making a significant contribution in the electromagnetic properties of superconductors. And so I can imagine Fritz and Heinz working together in North Carolina, taking walks around the beautiful countryside and thinking about London forces and superconductivity. So we can break down these interactions between polar molecules into dipole-dipole, which are Keesom forces, or dipole-nonpolar, which are the Debye forces. So it's important for you to know the names, but it's really important for you to know the situations because we describe each of these interactions in a different way mathematically. And so in the dispersion interaction, remember that W, right here, W is energy, so the energy of this van der Waals interaction for dispersion interactions is described by this equation right here. We will go through this equation in class, but what I want you to note specifically is the term right here that's related to 1 over r to the 6th. So you see this term at the end that's r to the 6th, and that describes the energy as a function of distance. So r is the separation distance between interacting atoms, and so the energy W as a function of r is proportional to 1 over r to the 6th. So think about what that means mathematically as a function of 1 over r to the 6th. We know what a linear function is, so we have a straight line relationship between x and y variables. We know what a exponential relationship is, so we can plot an exponential on the xy plane. But we can also plot a 1 over r to the 6th relationship. And that's highly nonlinear, so nonlinear is not a linear function. And so what this 1 over r to the 6th tells us is that if we have two molecules and we bring them close, that is a very strong attraction. And then as we move them farther and farther apart, the energy between these two molecules decays as a function of 1 over r to the 6th. Now that's a little bit different from the Lennard-Jones potential that I showed you previously in class, but it tells us that as we move these molecules closer and further apart, there isn't a linear relationship between distance and energy. And that's really important for you to know, and it tells us that the energy between these two molecules, or the energy of the dispersion interactions, is very high when they're very close and drops off very quickly as we move the molecules further apart. So why don't you think about 1 over r to the 6th relationships, maybe try and put it in Excel so you can see exactly what that function looks like. Of course, there's a limit. As soon as we push those molecules too close together, they'll bang into each other and we'll get repulsive interactions as we saw in the Lennard-Jones potential. So think about this mathematical relationship because it's an important concept in these intermolecular interactions. So we can also do the same thing for orientation interactions. So you can look at this equation right here, and it tells us that the energy of the orientation interaction is a function of r, and that's exactly what this says. So W0r is energy of the orientation interaction as a function of separation distance, is now due to the dipole, because orientation interactions are dipole-dipole. So here is the dipole-dipole part. So we have to calculate the dipole moment of 1 squared times the dipole moment of 2 squared, and I'll tell you how to calculate dipole moments in a second. These other terms in the denominator are well defined. So we have the permittivity of vacuum, we have Boltzmann's constant, we have temperature, and you see this 1 over r to the 6th again. So we know that r to the 6th in the denominator gives us this 1 over r to the 6th relationship. So the only thing that's different between orientation interactions and dispersion interactions is that we need to calculate the dipole moment. So you see the numerator is different in these two equations because we have to account for the polarizability. So if you look very closely in dispersion interactions, there's alpha squared there. This is related to the polarizability. So London forces, polarizability is important. In orientation forces, the dipole moments are important. And we're going to quantitatively calculate these quantities on Friday. But now it's time to get familiar with the functional form of how we calculate these energies. And then finally we have an induced interaction. So we have again the energy of the induced, Wi as a function of r, is now the dipole moment u squared times the polarizability. And so we have one molecule that has a dipole moment. We have another molecule that has a polarizability. Remember, induced is a dipole interacting with a nonpolar molecule. So if we have, say, HBr, which has a permanent dipole interacting with I2, which is an induced dipole, this is an example of an induced interaction, and so we calculate the dipole moment of HBr, we calculate the polarizability, or we look up the polarizability of iodine, and then we can plug it into this formula right here to get the energy, the interaction energy. And again, you see this r squared in the denominator, which we'll explore that more, what r squared means, but you should, or r to the 6th, sorry, 1 over r to the 6th. So you should have an idea of what 1 over r to the 6th looks like mathematically. And again, that tells us that the forces are very strong when the molecules are close together. So in liquids and solids, intermolecular interactions are strong. That's what makes liquids and solids, or condensed phases. And when the molecules are far apart, the van der Waals forces are weak, and we know that the gases, the molecules on average are far apart, and so there are weak van der Waals forces in gases. And it's all due to this 1 over r to the 6th relationship between energy and distance of the molecules. And so what we can do to calculate the total van der Waals interaction energy is just sum them up. So you can look at this slide and we can sum up the dispersion, orientation, and induced interactions. I can write this down on the board for you, but I think you're smart enough to sum up the different numerators and collect them under the same denominator, because they all had 1 over r to the 6th. And so now we can break down the interactions between polar molecules in terms of their orientation, dispersion, and dipole-dipole interactions, or induced interactions. And so we have this columns right here, these columns for these different molecules. You can look at this when you're thinking about chemistry on Wednesday or Thursday night, and you can look at the different molecules in this table, and you can look at the magnitude of their different van der Waals interactions, the dispersion, the orientation, and the induced, and you can start to think about, well, why does the neon-neon interaction not have any induced interactions? And of course there's no dipoles in neon, and so there can't be any induced or orientation interactions. Whereas water-water interactions, since there are two polar molecules interacting with one another, you have induced, orientation, and dispersion interactions. So in this slide they're using C, or the coefficient for the van der Waals interaction, but it's the same idea. So this coefficient is related to the energy, and so now we can think about how different molecules interact and what the magnitude of the van der Waals interactions are between these different molecules and how that leads to different material behavior. And again, neon and HBr and water are not necessarily materials that we'll use every day to build bridges or build buildings, but if we understand how these molecular interactions work, we can expand this to real materials. How does barium titanate work? Or how does steel work? Or how do polymers work? And so we'll make the relationship, or we'll make the connection between these van der Waals forces and the behavior of materials on Friday. For instance, one of the things I study is polymers. You know that. And so if you want to build a very high strength plastic part for an engine compartment, what you use is you use nylon, or you use filled nylon, or high temperature nylon. You don't use a molecule like polystyrene or polyethylene. And the reason is that polystyrene and polyethylene have very weak mechanical properties because the van der Waals interactions between styrene molecules or polyethylene molecules are low compared to nylon. Nylon has hydrogen bonding. It's a polyamide. I'll show you that structure on Friday. So for polymers that have very strong hydrogen bonding, they're very strong high-strength materials. Whereas polystyrene or polyethylene just have dispersion interactions. So they don't have any hydrogen bonding, and they have weaker intermolecular interactions between the chains, and so they're weaker polymers. So as one exercise, you can Google polystyrene, you can Google nylon 6,6, and you can figure out what their chemical structures are, and you can see why nylon has hydrogen bonding and polystyrene doesn't. So now Raymond and Clara will give you a little in-class exercise, and you can meet up with your teams. I'm sorry I can't be with you on this Wednesday, but please look at the slides and be ready to go on Friday. We'll see you soon. Bye-bye.